So now we're ready to move on to chapter 6. The next chapter is momentum and collisions. And what we're going to find here is that every bit of the math and the relationships that we've put together and built on in the last 5 chapters are going to be used in this chapter, and we're going to develop them to look at something called momentum and understand how we vectorially handle these, how we use the motion equations to determine momentum, how we use force and energy and power. It all comes together. So dust off your toolbox and be ready for an exciting ride. So we're going to look at momentum and impulse. Momentum then dealing with an object that's moving. The impulse is actually the point of time when the object is put into motion. We're going to look at conservation of momentum and energy and determine when momentum and energy are conserved and when they are not. And then finally, we'll look at collisions and glancing collisions and start to look at the categories of collisions like elastic, inelastic, and perfectly inelastic collisions. So let's start with the definition. The linear momentum of an object of mass m moving with a velocity v is defined as the product of the mass and the velocity. So you see here we've got a little p, little lowercase p, that we use to define what momentum is. It's not the lowercase rho like we saw before. It's a little letter p. 3 dashes is definition, and mass times velocity. The thing I want you to start thinking about as we progress is that we've got a scalar, the mass, times a vector, the velocity. So we will have x and y components associated with the velocity. Momentum then is a vector quantity and is a direction, its direction matching that of the velocity. And we saw before that we can multiply scalars and vectors together to come up with a new value that matches the velocity and the direction. So if we go back to our fundamental units here, we see momentum has fundamental dimensions of 1 unit of mass, 1 unit of length, divided by 1 unit of time. And so when we look at this in terms of the SI units, we have a kilogram meter per second squared. If we cut this in half right here, the kilogram is our mass, meter per second, I said squared, meter per second is our velocity. Meter per second squared would be acceleration, okay? Mass times acceleration, we'll get to that. So components of momentum then, if we look at taking them apart, momentum in the x direction, momentum in the y direction. And we will treat them separately, especially when we get into collisions and glancing collisions. So, remembering Newton's second law, force is equal to, in this case, the change in momentum divided by some change in time. And so if we decompose the change in momentum into velocity final and initial times mass in each case, we would have this relationship divided by time. Since the mass is the same on both of those terms, we can factor it out, and we get the change in velocity over the change in time. And so this is something we already know. Velocity over time is, in fact, our definition of acceleration. So the velocity of an object moving with a constant acceleration varies with time. So let's go back and choose one of our motion equations. Velocity final is equal to velocity initial plus that acceleration times time. If we manipulate the terms, move the velocity to one side, move the acceleration and time to the other, and then factor the time back over in the denominator, we end up with a new definition that says force is equal to mass times velocity final minus velocity initial divided by time, or very simply, since that's acceleration, mass times acceleration. So we've taken a step back, taken a step forward. The time rate of change of momentum of an object then is equal to the net force acting on the object. So we can take a look at this. Again, when we see net down here, we know we're talking about something that's put together component-wise, X and Y. So what is this impulse? We talked about momentum, and then we talk about the impulse momentum. Well, with momentum, there's always motion. And we have to look at the time-wise relationship that occurs when an object is at rest, gets hit, and starts into motion, and that motion then becomes the momentum, the mass times velocity. So with the impulse, we're looking at what happens when an object gets hit and it just makes contact. The force starts to build on the object, and as you follow through, the object moves away with its momentum. So we define force then as that change in momentum over time. If we factor the delta t out of the denominator so that we have force times delta t is equal to the change in momentum, again, over time, mv final minus mv initial, we end up now with a new term that we call the impulse momentum. So the impulse momentum, or the impulse, is defined as the force that occurs over time. So if we look at this graphically, where we've got a curve that we can use to model what's happening here, you can see that over time, initial to final, we've got a force that follows this bell curve to some maximum amount, and then the force starts to decrease back to some minimum. So a force acting on an object will vary with time. The impulse then is the area under the curve. We want to gather all of that force and classify it as that value that is represented by the area under the curve. So we could very easily go through, if we knew each point, each tick point on here, and these become rectangles, length times width, length times width, length times width, all together, add it up, and we could come up with a pretty good value of the amount of area under the curve when we add these together. We could take each of these rectangles and slice them in half and in half and in half so that we would have the whole area under the curve looking green. And if we knew how many of them there were, and we added them together as infinitesimally narrow, but having some length, we could come up with a value for that area. And this is the basis for what happens in integral calculus. Integral calculus is all about doing things like finding the area under the curve. So what if there were an easier way? Well, if we look at the definition of an average force, we notice here that we've got the average force down here, which is just about the halfway mark, over that same interval of time. The average force then, the horizontal dashed line, all of the area in yellow, gives the same impulse to the object in the time interval delta t as the real time varying force of the previous graph. So the impulse imparted by a force during the time interval delta t is equal to the area under the force time graph from the beginning to the end of the time interval, or equivalently, the average force times time. And if we look at that graph and that rectangle, if we were to cut that part off from the bottom, fold it up into the top, we would have just about the full area under the curve defined. So what we're going to do now is we're going to take a look at an example. This is an interesting example of what happens when a golf club hits a golf ball and puts that golf ball into flight. We have momentum and we have an impulse momentum.